Hi everyone, we're just figuring everything out, so we should start in a minute. Let's see. Okay, let's see how to. I don't know if I can create a new whiteboard. Yeah. So can people see my whiteboard? Yeah, I think people are following. That's good. Let's see. Here's the whiteboard. Transcribed. Okay, sure. Hello. There are more users on the whiteboard. Yeah. So can everybody see the whiteboard? Can I get a yes or no in chat, please? Yep. Yes, perfect, perfect. So it seems everyone can see the whiteboard. Yeah, so we can get started. Hi, I'm Anand, and I'm one of the coaches for the Indian IMO team and also for many other teams globally. Also, we'll appreciate if people don't, if people don't use the whiteboard, because I think if you have stroke marks everywhere, it'll make it difficult for others to follow. So I don't know if there's a way of disabling whiteboard access or something where there's no editing, but yeah. Okay, looks good now. Yeah. So today we'll be doing something related to SLMC, but I think it was just more for fun, where we will doing more logic and problem solving type of puzzles, where I think these problems do come up in contests, but they're interesting by themselves. They're similar to sort of old riddles you see. And there's a pretty interesting fair bit of mathematics which goes into thinking about them, or the kind of problem solving which goes there. So I don't know, has everybody seen the handout which I sent out yesterday? Does everyone have access to that? The problems? Uh, just like a yes or no in messages, please. So has everyone seen the handout? Yes. Okay. Okay. Perfect. I'm getting a yes in chat, or like a DM. Sounds good. So yeah, so we can start in the chronological order of the handout, I guess. And because this is more for logic and problem solving puzzle step handout, you don't really need to have the specific age limit. So it's applicable for all grades from like the earliest to the latest grades. I think everyone can enjoy these problems or think about them. So there's not like very sophisticated maths which goes into solving most of these problems. But it's still quite tricky. All these problems are still quite difficult. Yeah. So we'll start there. We'll start with problem one. And problem one is about this island of knights and knaves. So this is a pretty classic trope of an island with knights. Knaves. So knights are people who always tell the truth, and knaves are people who always lie. And that is important information, because if someone can sometimes say the truth and sometimes lie, then it's really hard to tell what inference you can make from their statements. But if you know for a fact that someone always says the truth or always lies, then you can make deductions based on that. Like then you can look at their statement and try to infer more information than it seems obvious from. So yeah, so this is a very common setting for many logic puzzles, and it's quite related to the idea of logic gates as well. So later on, if you study logic in a more sort of formal, symbolic way, then these problems can be encoded in that more technical language. But for our purposes, we won't do that because that's not very intuitive, and it's also more like you need a couple of classes to do that as a course, versus you can just think about these logically without having to sort of write bad notation. Yeah. Also, if at any point anyone has ideas that they want to share about any problem, if you want to like jump in, that's completely fine. So just like raise your hand or like say something in chat. And if you want to say something or ask something, that's completely fine. Or if you want to present your own solution as well, or which is maybe that's a different, that's all good. So if at any point you feel the need to do this, that's perfectly fine. So we have three people ABC that you meet on this island of knights and knaves, and A says all of us are knaves. Yeah. And okay, so apologies for the shaky handwriting, but I'm using a trackpad, so it's not the best. And B says exactly one of us. Is a knave. Yeah, so this is the statement of the first problem. And C does not say anything. You don't talk to C. So just based on these three statements, what can you say about ABC's types? That's the problem. So it's pretty interesting. You don't even talk to C, and A and B say some very vague things, which are not like, they don't really seem that they should be good information. But turns out just from these three statements, you can actually tell what type each of ABC is. So let's look at A statement first. And generally, in such kind of logic problems, the main thing sort of being tested is that if you can plug in the true or false values of a statement and deduce from there. So you can sort of do a casework where you can start anywhere. It doesn't really matter. For example, you can start from A statement and see what that means. So if someone says they're all knaves, okay, then A is also claiming himself to be liar. So the bare minimum A is saying that is that A is a liar, and then B and C are also liars, right? Now, no truthful person, no knight can say that they're a liar because that's a false statement. So this implies A actually has to be a knave. Also, there's a bunch of other cursor pens. So yeah, please just don't do anything on the whiteboard. Yeah, thanks. Yeah, okay, perfect. Yeah, okay, so very big implies arrow, but okay, sure, I'll get rid of this. Yeah. So when A says all of them are knaves, A is at least saying that A himself is a knave, right? Or A herself is a knave. So if A is calling themselves a liar, no knight can do that. Like knights cannot say that they are liars because that will be a false statement then, right? So A has to be a knave. Yeah. But then that's not enough. You can actually use this deduction again in some sense. So if A is a knave, then this statement is as well as false. Then the statement that all of ABC are knaves is also false. So what does it mean to say all of ABC are knaves is false? The sort of negation of the statement would be not all of them are liars. So at least one of them is truthful, are knaves. So we have one knave, which is A. Both P and C cannot be liars, is what this is saying. And C has not said anything, so we can't really look at C's statement, which means we should look at, yeah, which means we should just look at B statement. Yeah. Can everybody still see my whiteboard? Because it's saying following paused for some reason. Just asking, can everybody still see my whiteboard? Yes, okay, that's good. Yeah. Okay, sounds good. Yeah. So now we look at B statement. So we know that at least one of B and C is truthful, but we don't know which one. And we have to look at B statement. Let's say if B was a liar. So if B is a knave, like let us assume that if this happens. Yeah. So if B is a knave, what can we say then? Then B statement must be false, right? So exactly one is a knave is false. And if B is a knave, then you'll have two knaves so far, which will mean that for I'm the host now. Okay, so I think someone left. Oh no, SLMC is back. Okay, it's good. Yeah. Okay, so we have two cases, right? So we are trying to deduce things about B. Either B is truthful or B is a liar. So let's say if B is a liar, okay? Let's assume B is a liar. So if B is a knave, then we have two knaves so far. And B statement is that exactly one is a knave, right? Oh, sorry, I miswrote B statement. Exactly one of us is a knight. Sorry, I miscopied the statement. So if you look at the problem statement, it says exactly one of us is a knight. Okay, that's what B statement. Yeah. So when B is saying exactly one of them is a knight, then if A and B are both knaves, an A statement is correct, or A statement is not correct, that means C must be a knight in that case. So this will imply C is a knight. But then that will imply B statement is actually true, that there's exactly one knight, because B is a knave, A is a knave, and C is a knight in that case, which will imply B is not lying. B not lying. And knaves always lie, right? So this can't be true. Contradiction. So this is a contradiction. Like B has to be lying, right? And so B being a knave is impossible, because if you assume B was a knave is a true statement, then you end up with a contradiction. So this implies B is a knight. And if B is a knight, then B statement is true, right? So if B is a knight, then B is not lying, which means exactly one of them is a knight, and B is the knight we know of. So B is the one knight, and then A and C have to be knaves. So the correct conclusion is that A and C knaves, and B is a knight. And this is sort of the solution for this problem. And notice that there's lots of intermediate steps. It's not like it's very straightforward to do this. You can get lucky, for example, if you just guess correctly. So you can, in some sense, guess that if A is a knave, B is a knight, and C is a knave, if you guess this as your configuration, then you can check that A and B statements are true. So that's one way of doing it. If you're doing it like a multiple choice contest or something, if you happen to just guess it correctly and just verify that the statements are correct, that's fine. But that's not very instructive. Like you don't learn much from verification alone. In this case, you actually learn from the process of thinking about it. And we have different ideas. So it's like there's some statements where just by the statement themselves, you can tell something about the person. So for example, a knight will always be obligated to call themselves a knight. A knave will also always be obligated to call themselves a, to call themselves a knight, right? Because a knave won't say they're a knave. That will be a true statement. But when A, so if A said I'm a knave, that would be a problem. That would be a sort of self-looping contradictory statement. But because there are other people involved in that all statement, we couldn't deduce that, oh, A must be lying in the first place, but some other person in that thing would be, yeah, not all of them would be knaves. So there will be a negation of that. So would be a knight. Yeah, exactly. So A is not themselves a knight, but somebody else would be. And then from B, you can say, okay, now we can analyze for B and do a similar case work. We chose so intentionally we chose the case which is not that good, which is going to lead to a contradiction. And that's kind of how you deduce these things. Is you assume a truth value, you go through the whole process. And if it's not the correct configuration, if it's not going to be a viable configuration at the end, then this will give you a contradiction at the end. So then B will actually give you a contradiction if you assume B is a knave, unless there's multiple possible solutions. So that's usually not possible in these problems because they're by design supposed to have, let's say, one configuration which works and everything else does not work. But if there are multiple configurations, then of course you can have different types of things. So that will be a more sort of sophisticated problem. But in general, you should be able to start from any point and make all possible deductions if you can. And that should net you the final unique idea or final unique configuration of knights and knaves. And that's the general idea for these problems. That's a general strategy. And the techniques used are very similar. So either you look at the same statement and infer something from that, or you look at the statement and sort of look at, assume something about that statement, either it's true or false. And based on the true or falseness of the statement, or based on the assumption whether the character is knight or knave, you can make deductions based on that. You can say that, oh, either this is a contradiction, and if everything is consistent, then this is probably part of the configuration, but we don't know. So contradictions are much more reliable because they rule out something and then let you deduce stuff. But if you just, for example, if you assume B is a knight and you get a valid configuration, that tells you that ABC being these things is possible. Okay, so maybe it's actually an important point worth pointing out. If you had started this proof by saying, or if you had started the solution by saying, if B is a knight. So if B is a knight, and then you'd never had any problems, right? Then you would have A and C are knaves immediately. You don't need any contradiction. Implies A and C are knaves based on just A statement, and B statement implies B is the only knight. And there's no contradictions. So this is proof that this is a valid configuration, that this configuration is something where these statements are consistent, but this is not proof that this is the only valid configuration. So at the level of a multiple choice contest, you don't really care. You just want to find the correct configuration and take that choice if that's a single choice thing. But at the level of doing accurate mathematics or precise mathematics, it's important to be able to tell that, oh, you want to actually prove that this is the only thing which can happen. And yeah, that's that's what we did here with the idea of going by a contradiction. Yeah. So we assume that if B is an if, then yeah, then the statement must be false. And so exactly one night among us is not true, but then at least one has to be there. So, and both of them can't be there. So that's a contradiction. Yeah. Okay. Everybody okay with problem one? Everybody comfortable with that? Just like a yes or no in chat, please. Or if you have any questions about problem one, we can talk about that. Yeah. So if you have any questions, or if you want to talk, no questions, okay. So I'm getting lots of DMs, no questions. But if you have any questions, anybody, you can just like unmute, you can DM or anything of that sort. All good. Yeah. Or if you tried something different, if your approach was different, that's also completely fine. But if I was to give you like two takeaways, even if we don't look at the, or you need the handout. I asked Professor Chanak, let's see. I'll just ask him. Maybe there's a way for me to put in the chat. Let me check. I mean, I have a copy, but I don't know how to put this in chat. Let's see. Meeting group chat. Is there a way of putting PDFs in this thing? Let's see. I don't think there's a way of putting PDFs in this thing, unfortunately. Or can I touch a file? Oh, that's possible. I don't know. I've not used this setup before, so let's see if there's a file. There's a file attachment thing. Let's see. SLMC. Yeah, I think that should be it. So I'll push this in the. Okay. I think this should be it. Yeah, thanks. Thanks for pointing it out. I think this will be useful for everyone because it'll be quite dangerous if I just discuss everything and people don't have access to the problems. That would be quite bad. So thanks for that. Thanks for no. Yeah. Can everybody see this in chat? The 12 problems? The problem set? Just like a yes or no, please. Yep, perfect. Sounds good. Yeah, perfect. Okay, so now we can move to the question two, which I think is probably more interesting. It's also from one of the American math competitions, and they have a similar variety of questions, but this was pretty interesting, I think. So if everybody can read the statement, they'll save some time, but let me go over it just so I also remember what the statement was. It's not very, yeah, I don't fully remember what the statement was. Let's see. Yeah. Okay, I have all the, yeah, the statement with me. It's 40 slips of paper. Yeah, so you have 40 slips of paper. So you have 40 slips from 1 to 40. And you have two people who pick from these slips without replacement. So A and B are two people who pick these things, and they do it without replacement, which means that I can't pick 23 twice. So I can't pick the same slip twice. Yeah. And they keep the numbers hidden from each other. So A and B keep the numbers hidden. And then they make the following statements, right? So Alice says, okay, so Alice says, I can't tell who has the larger number. And then Bob says, I know who has the larger number. Alice says, you do. Is your number prime? And then Bob says, yes. Alice says something else. In that case, if I multiply your number by 100 and add the result is a perfect square. So a bunch of statements. And it's quite surprising that you can figure out what the numbers are from just this conversation, which is completely cryptic. And so it's actually not that cryptic. Like it is something which is quite reducible, right? So Alice's first statement is that I can't tell who has a larger number. And so you might say that this is not very useful information. Like, what do you mean I can't tell something? Like, how is that useful information? If somebody else's number is hidden, then also I also can't tell. Right? I can't tell who has larger number. So it comes off as a surprise that you can infer anything from this statement, right? Because if you just say, I can't tell who has the larger number, sure, a bystander also can't tell who has the larger number, right? But this actually does have some information hidden in it. Because in some cases, you can tell that the other person has a larger number. So those cases are not happening. And that's the point here, is that, so I'll just say, this is the point. So actually, in some cases, yeah, so, thanks for correcting that. Send the PDF again, please. I think it's in chat, right? Yeah, I think I pushed this in chat. You can see in the common chat. I think it should be in the common chat. Just check if it's there. Yeah. So actually, in some cases, you can. So you can deduce who has the larger number. So this means that Alice does not have one of those cases. So what are these cases? Well, if Alice picked the number 40, yeah. So someone DM'd me. Yeah, you have the correct answer. You have the correct answer. Yes. So I will not spoil it further. So we'll go over the process, but you have the correct answer. Yeah. So actually, in some cases, you can deduce who has a larger number, right? So if Alice picked the number 40, she knows she has a larger number. And if Bob picked the number, or if Alice picked the number 1, then she knows that Bob has the larger number. So there's no ambiguity in these two cases. So Alice's number, if we call it A, is such that A is bigger than 1 and less than 40. Like it has to be anything other than 1 and 40, right? So there's actually some information. It's a very sliver of an information, but there's some information that it can't be these two. Otherwise, she would know. So she would know who has a larger number. And so we have to rule out those two cases now. Now we're getting somewhere. Like now we have some more information than just like a completely blank thing. Yeah. Okay. So now we can go to Bob's statement. Like, what does Bob reply to this? He says, I know who has a larger number. So he says, I know who has a larger number. Yeah. Which is a strange thing to say now. So how does he know? So it means that he must be in one of those edge cases, right? So he knows that, okay, if Bob had number 1 and 40, then he would know who has a larger number. But he also has this information, right? So he has this information that 1 is less than A less than 40, right? So he knows Alice's number is in this range, which means he knows who has a larger number. Could only be that if he has the number, yeah. So if he has the number 1, 40, 2, or 39, if this is B, if B is in one of these things, then he knows for sure, right? Because if he has 39 or 40, he knows he has the bigger number. And if it's just 1 and 2, then also he knows he has a smaller number and Alice has the bigger number, right? So these 4 are the only possibilities for Bob's number based on his statement. Now Alice asks something else. He asks, you do? Is your number prime? And he says yes. So the only prime number in these 4 is 2, right? So Bob's number has to be equal to 2 now because of his statement. And now Alice says that if you multiply Bob's number by 100, so if you look at 200 plus Alice's number, which is 200 plus A, this is a perfect square. This is a square of something, right? And can you think of a square which is bigger than 200? So it's bigger than 200, less than 240, which means it can only be 225, which is 15 square, right? So this is 225, which means A is 25. So Alice's number has to be 25. And then the sum of their numbers, 25 plus 2 is 27, which will be the final answer they want. But yeah, that's easy enough. The hard part was figuring out what these numbers are. Yeah. So does everybody understand the idea of this problem or the solution here? Why are 39, 2 and 39 included in the possibilities of Bob's number? Good question. So if Bob's number is 140, he knows who has the bigger number. But also, after Alice's first statement and his first remark that Alice's first statement that she doesn't know was the larger number, he actually knows Alice's number is between 2 and 39. So his number could be 2 and 39, and he still would know which one is bigger. But for example, if Bob's number was 38, then he wouldn't know, right? Because Alice's number could be 39. So if Bob's number was 38, then he wouldn't know. And similarly, if Bob's number was anything between 3 and 38, then Alice could have either 2 or 39, and he wouldn't know in either case, right? So it has to cover 2 and 39 for him to know. so it has to be 2 and 39 along with 1 and 40 in this set for him to know for sure. Does that answer your question? It's a good question. Yeah, that's a good question. It's good to point that out. So, and you will notice something interesting in here. Not only does Alice deduce this because she's a perfect logician, not only we infer that 1 is less than a less than 40 based on Alice's statement, Bomb also deduces the same thing from the statement. Like he's able to tell from the statement as a sort of perfect logician that Alice's number must be between 1 and 40. Like it's bigger than 1 less than 40. So it's not equal to 1 or 40. And that's kind of a recurring theme in these problems is that not only do you have the information which the person says as a statement, you have all the information which can be deduced from all of the previous statements. Like both characters are supposed to have all of this information. That's the only time they make the next statement, next logical statement, unless you're told that one of those statements is a lie or something like that. So it's pretty interesting because you can sort of do the whole thing of I know that you know that I know this whole like there's a movie trope as well, right? Where people are able to predict the action of other characters. And that's kind of the idea here as well, that you're able to, like Bob is able to tell what Alice was able to, what one can deduce from here. And so he was able to say this. And then because he said this, then Alice can deduce this. We can also deduce that the number must be 2. And Alice did deduce this as 2. And so she said 200 plus a is a square to give away her number as well. It's also why this is actually a pretty funny example where you can have a very cryptic looking thing. Like it looks like something is properly encoded, but it's actually not encoded, and you can break past the security of the thing, let's say. So this conversation looks like it doesn't give away any information, but it actually tells all the information anybody could want, right? So you have to be a bit more careful, I guess, in communication. That's also one idea. But the main idea is that everyone involved in such logic games is able to deduce perfectly from everything which has been said prior. Like everything which has been said before can be deduced perfectly now onwards to the future. So this is something which you should keep in mind when you are approaching these problems. It's a good thing to keep in mind. So which problem do people want me to try next? Because we have about 10 more problems to go through. I don't know if we can go through all of them today. So let's go through like the popular problems, like which ones students find more interesting. We can discuss those. Wait, what happened? Where did the page go? And I'm not sure what happened. Something strange happened to the whiteboard. I think the page disappeared or something. For some reason, what we typed so far disappeared. I don't know why that. I'm on my cursor's on the other end of the world. Okay. Yeah, okay. Sorry, my bad. Yeah, no, okay, the cursor is on the other end of the world. Yeah. Okay, sounds good. So is everybody able to see the whiteboard? Because can you try question 5? Sure. So we can look into question 5. What is the statement for that? Yeah, question 5 I think is quite fun. It is extremely fun, I have to say. Yeah, so can I speak slowly? Yeah, sure. I'll try to. I am told I speak very fast, so I'll try to say things slowly. Yeah. Okay. Third question. Okay. So there's demand. Okay, maybe we can do a little bit of a poll. So maybe I'll push this in chat. Which question should we do next? So 3 PDF again. Let me see how to send the file again. File and SLMC. Can you send me the people of the questions? Yeah, no, I put this in the group chat. I think this should be accessible. So yeah, and we're doing a poll for question number 3, 4, and 5. Let's see which one people want to do. I think all the puzzles are pretty great, but depends on. We can go through all of them slowly. So there's votes for 3, there's votes for 4, and there's votes for 5. Like right now, it's a current tie. It's a 3-way dead heat tie. So yeah, okay. There's more votes for 5. Let's see. So yeah, so if people can maybe you can do this. If you do like a thumbs up, it's 3. If you do like any other emoji, it's like 5 or something like that. I don't know. Yeah. The for the 3, 4, and 5. Yeah. So all 3, 4, 5. Okay, all 3, 4, 5. Okay. So, but which order? Let's start with 5, and then we can move on to like 3 and 4 as well, or we can see what the atmosphere is, because 5 so far seems to have the largest number of requests. Like 3 and 5 is a tie right now. So okay, yeah. So yeah, let's start at 5 first, and then we can talk about 3. Because I think 5 is conceptually more interesting. 3 is more fun as a puzzle type of thing. P3 from IM 2017. Yeah, tough. That's tough. And then that'll probably take a few more lectures, I would say. But yeah. Okay. So yeah, let's do P5. I think P5 is actually quite fun. So P5 has 3 parts. So the first statement is that if 2 plus 2 equals 5, then I am, and I can be for anybody in the room, if they want to read it that way. So then I'm Santa Claus. So this is almost a joke in some sense, but is this statement true or false? That's the question. So can someone, actually, I'm curious, like, can someone say this in chat, common group chat? If you want, you can just say, whether do you think the statement is true or false? So can we have a poll on whether the statement is true or false? False. Okay, so true. Okay, so I have a bit of both. Okay, so I think people are generally making the correct answer. So the idea is that the statement is actually true. And the deeper idea is that if you assume something which is false or something which is vacuous, then anything is true, right? So false always implies true. Like if you have a false statement, that always implies then anything is true. Anything is true. So if you assume a false statement, then anything can be true. That's generally the case. So this is a true statement. And how do you prove something like this? So let's consider okay, that'll be quite funny. Uh, no, it doesn't even have to do with the fact that Santa Claus is a myth. Like that also doesn't even have to do with it doesn't even have to do with that. Like it's literally, you can replace Santa Claus with like any human character. So you can replace him with, I don't know, like Tom Brady or something, and you can still say the statement. It'll still be true. So yeah, because 2 plus 2 equals 5 is false. Like that's the thing which actually gives you the problem, not the Santa Claus part. So you can replace it with the real person as well. It'll still be false. It'll still be true as a statement, because the presumption is false. And so you can think of it as follows. Uh, let's see. Can you suggest names of people where we agree that these people are different from? So I and Santa Claus. So these are 2 people. And then I have 3 other people here. Okay, maybe I won't even put them as people. Let's actually literally do this thing. Let's do this thing where I'll have a chair, a pencil, and an iPad. So look at this set of 5 things, right? So the set has 5 elements. Yeah, but 5 is equal to 2 plus 2, which let's say we know this is 4. So this is all a joke. This is really just a joke way of showing that false implies any true statement. So this will imply that, okay, none of these 3 things are same as any of these 2 things. So these 2 must be the same. Must be the same. So it's a bit of a joke. It's really just a way of saying that if you assume something which is incorrect, which is just false, then you can say pretty much anything afterwards and that'll still be true. So that's actually not a proof. Like to give something which counts as not even reasonable, just like a decent or just as a correct thing, is that you always have to assume something if, and this thing in the if has to be true. When you assume that, then you make a deduction, right? So this implies something. So if your if statement, this part is false, then everything that follows will also be, you can just say anything afterwards. It doesn't matter. So when you make correct logical inferences or deductions, you always have to ensure that when you say if, the thing which follows is actually true. So for example, yeah. So for example, okay, if the statement was flipped around, if the statement was if Santa Claus is Santa Claus, then 2 plus 2 equals 5, that is a false statement because the if part is true, and then the part which follows in the then part is false because 2 plus 2 is not 5. So that statement would be false. So you have to be careful about this. And that's kind of the whole point of this problem is that you can look at this set of five things. 3 of them are different from any 2 of these things. So because 5 is equal to 4 in our assumption, this implies that these 2 things must be the same. And you can pretty much do this for anything. Any false thing you can use to reduce anything at that point. You can go from false to false. You can go from false to true. None of that counts as a proof because from false you can go to anything. Yeah. So this was part A, which is mostly just to test, sort of this feeling of if something is false, how do you understand that statement? And the next part will be dealing with more like vacuous statements, which is also, I think, more of a joke. Yeah. The next part is actually more interesting. So let's say you have a school, and so you have schools A and B. Wait, where did the thing go? I'm confused. Where did the whole thing go? I'm not able to find it. My cursor, I think, moved again or something. Uh, yeah. So if you assume something false, like if you assume that if you assume, let's say 1 is equal to 2 or something, then you can reduce anything you want from there. Then you can say pretty much anything, and that the thing you say after does not have to be true or false. But the point is that this whole statement as a whole, if false, then anything, this statement is true. So it's a bit trippy in some sense, right? Because the thing so you can verify the truth value of things in the if and things in the then. But when you combine this whole sentence, if the if part is followed by a false, then the whole sentence is true, regardless of what the then part is. So it's a bit trippy, it's a bit confusing, but that's it's also a good way of familiarizing yourself with why you should always assume true things. Like if something you're assuming, then that thing has to be true. You can't just assume something which is blatantly false. Okay, let's see. Where did the thing go? Like I can't find where I wrote things before. Like my cursor has completely gone away. I see like a red dot somewhere, which is I don't even know. I just see like random scratches somewhere, but I don't see anything on my screen. So I don't know what happened. Yeah, I don't know what happened with the whiteboard. Can people see the whiteboard? Don't choose. Yes, you can see the whiteboards. Okay, wait, can you see me typing, writing anything on the whiteboard? I've written an H on the whiteboard. Yeah, okay, that's good. That's good. Yeah, okay. Yeah, something went wrong with the whiteboard suddenly. Like I don't see anything I wrote previously. It's just all gone for some reason. But I think it should be fine. We were discussing a new problem, so we didn't lose anything. So let's do the second part of 5. The second part is also interesting because it's not just about the kind of trickery we have been doing so far. Yeah. Okay. Yeah. This is also pretty interesting. If in a school, so you have if in a school, some students play cricket. So let's say there's some finite number of students and they all play cricket. Which basis where assumptions opposite is the basis? So basically the point is that if you assume, so when you're doing a mathematical proof, you can say something like, I assume that, okay, let ABC be a right triangle, then AB square plus BC square is equal to AC square. Okay, so you can say this thing. And then from this statement, this is the Pythagorean theorem, you can say with this, you can deduce something else. So when you're doing this in a chain where everything is true, that you're doing it from axioms which are correct, then it's fine. But if you assume something which is false from your own set of things you started from, if you assume something which is false, then you can say anything afterwards. So that'll still be a true statement. It'll not be very meaningful, is the point. So For example, you can say that if 2 plus 2 equals 5, you can say a true statement as well at the end. You can say, yeah, you can say pretty much anything which is true afterwards, and that'll still be correct. Like as long as the if part is followed by a false, you can say anything afterwards, and the whole thing as a statement is correct. It's just that the statement is not very useful. It doesn't say anything meaningful. Because it doesn't, okay, so the whole point is it doesn't tell you that the second part is true. It doesn't exactly tell you that. So what do we call this kind of proof? Oh, so it's not really a proof in some sense. It's more like the statement is true. So you're able to deduce that the statement is true, but that's only because the if you're assuming is false, right? So yeah, okay. So I'll go through the B part as well. So yeah, if in a school there are I'll just say some finite number of students, then and some of them play cricket. So some students play cricket, maybe others don't. So I imagine cricket is still popular, and other people don't. So other students don't. Then the statement says, then there exists a student. So this is a symbol for there exists. So I can single out one student such that if the student plays, so this student plays cricket, everyone plays cricket. Everyone plays cricket. So, okay, one thing I'd like to clarify is that it's already a known thing. So it's not like if people are joining in the cricket team, it's like, oh, what the statement, or maybe it could have been worded better, is trying to say is that, oh, you have some group of people who play cricket and some people who just don't play cricket straight up. So in the school, that's the if assumption. And based on this assumption, you're saying that there exists a student such that if the student plays cricket, then everyone plays cricket, right? So is this whole statement, you're not asking for any particular piece of the statement, you're asking if this whole statement is true. You're asking for this whole statement, right? And so the idea is that, so, okay, there's some false, there's some true. Let's see. Yeah, the idea is that, okay, if everyone plays cricket, you can pick a random student, and then if that student plays cricket, everyone plays cricket. So that statement is true. Sorry, you were saying? Yeah. But the tricky part is that, okay, what if, let's say there's like 10, for example, let's say there's 10 students and seven of them play cricket and 3 of them don't. Is that a counterexample to this statement, to this proposition? Not exactly, right? Because you can pick any of these 3 people who don't play. Like, let's say I pick one person who does not play, and then this compound statement, this combined statement becomes equivalent to if this person plays, then all of them play. So all of them playing is false, but this person playing is also false. So you're assuming if something is false, then anything else, which doesn't matter anyway. So this is a true statement. This thing is also true. It's true in a strange way, but it's true. And the proof of why this is true is as follows. So you can split it into 2 cases, right? So case 1, all of them play. So if all of them play cricket, then the idea is that you can pick anyone. That person is the last person to join the game. Or false? No. Yeah. Okay. Yeah. So okay. So there's something in chat, but I think this period, yeah. So all play. So first case is if all of them play, in which case you can just pick anyone. So pick anyone, and the condition is satisfied, right? So then there exists a student such that if the student plays, everyone plays. That statement is true here. Case 2 is the more funny case where, okay, not all play. That's the remaining case, right? And so if not everyone plays, then there exists a person who does not play. So there exists a student, I'll call him C, who does not play. And now the following part is true. This implies if C plays, then everyone plays. And so this is what the statement becomes equivalent to. Or rather, this is the one instance we want the statement to be true in. And this is true. This is actually true. Because if C plays, then everyone plays is true. Because C does not play. So you're assuming something which is false. And so if C plays, when you know that C does not play, then everyone plays is a true statement. Could I see the letters? The writing is a bit tough for this. Okay, yeah. I'll try to maybe get like a thicker pen or something. How can you explain the yeah, I'll explain the second scenario because that's the more interesting one, right? So let us first understand what this compound statement is. It's saying in a school, some students play cricket, that's given to us. Then there exists a student such that something happens. So when you say there exists a student such that another if part happens, you're saying that across all the students, like if I pick student 1, student 2, all the way to student n, like the last one, if I pick all these students and look at these statements, if student 1 plays, then everyone plays. If student 2 plays, then everyone plays, and so on. Among all these statements, at least one statement is true. That's what the compound statement actually means. So this the correct interpretation for this statement is that if you go over here, then this statement says the following. If student 1 plays, then everyone, right? And then if student 2 plays, then everyone. I'll just do this comma double quotation thing. And so on. If student 3 plays, then everyone plays. All the way to the last student. If student n plays, then everyone. So this is what this statement actually means, that at least one of these statements is true. Yeah. So the point is that if you look at all of these statements, if student 1 plays, then everyone plays. If student 2 plays, then everyone plays. If the student n plays, then everyone plays. Among these n statements, at least one statement has to be true, is what the compound statement is claiming. Like this is what the claim of the compound statement is, right? And so in the second case, when you assume not all play, so let's assume that S2 does not play. If S2 does not play, then the second statement is true, because the second statement says, if S2 plays, then everyone plays. And S2 does not play by assumption. So if you're assuming a false thing, then anything follows. So yeah, it's just like, yeah. Simply because there does not exist a case where S2 plays and not everyone plays. Like there does not exist a counterexample to this statement. That's why it's true, right? So the statement is true in that case. Is there not a, yeah, like, it's basically like a recurring truth statement. I don't know what you mean by recurring truth statement. Can you explain that? I'm not very sure what you mean. But yeah, I should say the basic idea is that, okay, how do you know something is true? Like if S2 plays, then everyone plays, is a true statement when you know S2 does not play. Is that you can't give me an example where S2 plays and not everyone plays. Like if you can produce an example, then the statement would be false. But you can't produce such an example because S2 does not play. So you can't produce an example which contradicts the statement, which is why this will be a true statement if S2 does not play. And then you look at all these n statements, and every time at least one of these statements is true, which is what the compound statement is claiming. This is what this whole statement is claiming. And so this whole statement is true. And so it's a pretty trippy problem because there's like a lot of quantifiers involved, but that's kind of the point. Is like, I think if you try to meditate on this problem, you learn a lot about logical quantifiers. It's a pretty good problem in that sense. But the main case is the second case, because the first case is pretty obvious. If everyone plays, then all n statements are true. But if not everyone plays, then the person who does not play will give you, let's say, their person number j, then the jth statement is true. Yes, sure. I'll request Professor Chanak if there's like a similar translation or explanation. And that'll be very useful, I think. So I'll request him for sure. Yeah, but I hope the explanation makes some sense though. Like in the one currently we are having English is that the idea is simply that when you have a compound statement like this one, then or at least this specific statement, it means that among these n statements, at least one thing is true. And in the case when not all play, we are able to specifically pinpoint someone for which one of those statements is true. Is there a similar scenario to this to explain this idea in another sense? You can, but that will be, I think, roughly identical to this one, for example. So let me think if there's another example I can make up on the spot. So one thing you can say something like is, okay, so you can say something like, let's say you have real numbers A1 to, I don't know if everybody's comfortable with real numbers, so I don't know if this is a good example, but this is equivalent to the statement above. Let's say you have these n numbers, and you can prove the following. If several students do not play, yeah, that's the point. If several students do not play, you pick anyone who does not play. So let's say you pick, let's suppose S1 is someone who does not play, right? If S1 does not play, then the following statement, if S1 plays, then everyone plays, is a true statement. Because you can't give me a counterexample to this statement. You can't come up with something where S1 plays and everyone else does not play, because S1 never plays, right? So S1 doesn't play. So there's no counterexample to this statement, which makes this a true statement. And so that's kind of the tricky part here, is that if S1 does not play, then the statement is still true because the first part of it is false. Yeah. Yes, so it's a bit tricky. It's not very immediately clear. But the point is that if the if part of a statement is false, then the whole statement is true, regardless of what the then part says. And so you're just saying that, oh, in the case when not everyone plays, one of the statements has the first if part completely false. So then the whole statement itself is true. And you're saying at least one of these n statements are true. So you're combining all of these logics together to say that the compound statement is true in some sense. It's a pretty complicated way of looking at the world, but it is there. And you can come up with an identical analogous thing, where let's say if you have these real numbers, A1 to AN, then the following statement is true. There exists I such that, not unique, sorry, there exists I'll erase the, whatever this thing is, such that if mod AI less equals 1, then for all, so again, this is a very complicated way of saying the same thing, which is why I didn't want to come up with a more concrete example, but this is equivalent in some sense. Okay, mod AJ minus AK is less equals 2. And so the idea is that if all of the AIs are within 1, then this is anyway true. And if something is not, then you can just pick that AI because the if part will become false. Top of the board, we could only see the edge. No, you have to go down, I think. Like, I think you can go down with the cursor, right? I think you should be able to like scroll down as well, because edge was very much at the, I don't even know where edge was, to be honest. I think you have to go down. Okay, now I don't see my own thing now. That's a bit strange. Oh, now I see it. Yeah. Yeah. I think it's at somewhere in the, when you look at the lower bars, the lower bar is somewhere in the middle, and I think it's like both bars are a bit in the middle. So like the vertical and the horizontal bars to scroll down are both in the middle, and that's where roughly this thing is. Oh yeah, I don't think English knowledge in particular matters. I think it's like every language will have some grammar which will have, like, the logic itself will stay the same. It's just like the grammar will be different. So like the way to say these things will be different in different languages. So I can understand this being confusing. Like if you're, because the English used here is more sort of mathematical English, can be complicated. But I think there will be equivalent explanations, equivalent ideas in every language. Like there should be pretty much consistent explanations for this type of idea. So you don't need to worry about that. You don't need to worry about, like, this is more math than it has anything to do with English. So don't worry about that. Like I don't think English is the barrier, but yeah, I think it's hard to say this in a, it's hard for me to say this in a language I don't know, let's say. So yeah, I think that's the only thing I can say. But yeah, I think every language should have the equivalent of this type of idea. So you don't need to worry about language. And if someone asked me for another scenario, this is the other scenario. but it's not very intuitive. Like this is even less intuitive than the previous one. So yeah, I wouldn't spend too much time on it, but this is the same statement as the above pretty much. And you can go from one to the other. I don't think English is a barrier. I think many countries, in fact, I think I'm not too sure, but I think even the Chinese team writes the script not in English. So I think even very strong teams do not write in English. So English is not a barrier. Someone asked that, is English a barrier for IMO medal or something? But I don't think that's the case. I think you can be proficient in your native language and it's still going to be fine. It's just like, for me, it's hard to explain in any language I don't know. So I'm sticking to the one I know. Yeah. But yeah, they should be equivalent. So if we get a translation for today's class, then there should be some equivalent thing for all of this. So don't worry about it. Yeah, this one says that not true, right? Because this, yeah, no. So the point is that if S1 does not play, then the statement if S1 plays, then anything that follows after that is true. So if you're assuming if S1 does not play, then the statement if S1 plays, everyone plays is true, because the other statement is also if S1 does not play, then the statement that if S1 plays, then S1 is Santa Claus is also true, because the first part is false, right? So you're using A part sort of to get to the B part in some sense. But like if you say something which is false in the if part, then automatically whatever you say in the then doesn't even matter anymore. Right? So that's pretty much the idea in some sense. So like if you assume S1 does not play, yeah, then the statement if S1 plays, then S1 is Santa Claus. Like this is also true. Like S1 is not Santa Claus for sure, but point is that if you assume something which is not true, then you can say anything afterwards. It doesn't matter. So this whole statement is true. What you might be confusing is that you might think that I'm saying this is true. This part is not true. This part is not true. But once this part is false, then the then part doesn't matter anymore. The whole thing is true. So you're asking whether the whole thing in the quotation marks is true. This part doesn't have to be true. So similarly, when you go above, when you go here, when you say if S1 plays, then something, then everyone plays, the then everyone plays part does not have to be true. But if S1 plays already makes that the then part is irrelevant completely. And that's the idea. That's the idea of this problem. So it is pretty trippy. It's because it's saying a bunch of meaningless things. It doesn't say anything which is actually useful, but the statement itself is still true. So yeah. No, so the if is followed by false, then anything is true. So maybe the paradigm we can take away from this is that if and whatever is in that thing is false, then and you can have whatever be anything. Anything. It doesn't have to be true or false. This whole statement in quotation marks is true. What this does not imply, I'll make a crossover here on the implies, does not imply that anything is true. So you have to be a bit careful. So it does not imply this statement. Okay. And that's precisely the point, is that you don't deduce anything from these statements. Like these statements don't tell you anything, but they as a statement are true. They don't tell you anything. They don't say anything meaningful, but they're still true. For example, if 1 equals 2, then I am Santa Claus is a true statement, but I'm not Santa Claus, right? So yeah, I mean, for all you know, for all you know. So yeah. Okay, that's all we have for B part. And then finally we can do the C part. C part is a bit less confusing. So let's say you have two cricketers. Let's say I'm not keeping too much in touch with cricket right now, so let's just call them A and B for now. And in the January to December season, January to June season, A has a higher batting average. In the July to December season, A still has the higher batting average. Then from the January to December season of the same year, is this true? Does A still have the higher batting average? Is this still true? So can I have opinions in chat? It's actually fairly common in cricket or any sport discussions. This is quite common. Is it still true that from January to December, A still has to have the higher batting average? Yeah. Just from this information, you don't have any other information about number of matches or like when they played, where they played, nothing. Just like batting average of A is higher than batting average of B in the first part of the year, and then similarly in the second part of the year, it's also higher. For the whole year, is it higher? So there's a lot of yeses, there's a lot of trues, but you should also know that you have a problem with three parts, and there's two trues already, so you should have some suspicion that this may not be true. So yeah, it's indeed false. It's not a true statement. And I'll give you an example. So to prove that this statement is false, you just have to give an example, right? Like it's enough to give an example where the average of A is higher than the average of B for 2 seasons, but not for the whole year, right? So let's say B got 0 runs in one match, and that is the only game B was allowed to play in January to June because B just played really badly. And A got 1 run out of 2 games or something. So in this case, A has a higher average, right? Everybody agrees? Now let's say in the next season, A played 98 games and scored, I want to say, or okay, maybe I can make this slightly better. Not 98 games. I want to make it slightly better. So, okay, let's say, okay, this is 1 in 20. Let's say A in total played 80 games in the second part of the season and scored 80 runs. So 80 out of 80. And B in the second half played 99 games and scored 98 runs, right? So in both cases, we do have that A's batting average is higher than B's batting average. It's like 1 in 20 is more than 0 in 1, and 80 in 80 is more than 98 in 99, right? But when you take the whole average, this is 100 games total, and A has 81 runs, and B now has 98 runs over 100 games. So that is false. So this is false. Yeah. 1 or 2 months, the score will be lower than B. Oh no, when I say higher, the averages are calculated at the end of the thing. So it's not like we are computing a continuous average. We are computing averages at the end of the thing, like at the end of the season. The batting average from January to June. So, sorry, maybe there's some ambiguity. When I say batting average from January to June, I mean after June is concluded, that's when you calculate these averages. So maybe the statement should have been more precise in that sense. But yeah. Yeah. Yeah, but someone pointed out if both play an equal number of matches, it's not guaranteed to be true. Yeah, and that is indeed the answer. So because they played unequal number of matches, had unequal scores and unequal levels of performances, the thing was not true, right? And this is a good exercise in coming up with examples. Like one thing which you should always, when you're trying to verify something is true or false, not just do like this logical manipulation, which we did for the previous 2 questions. Sometimes it's good to just actually throw in numbers and do actual calculation by hand. And that'll tell you whether something is true or false. Because if something is true in like a very extreme example, you can be more confident it's true generally as well, right? So you can have intuition about what examples are good to choose from. It couldn't be the case that, okay, for example, if A was always leading B throughout, then A's average is still higher than B's average. That can still happen. So it's not like it's always false. Sometimes it's true, sometimes it's false. But as a general statement that A's average must be higher than B's average, the general statement is false. We can come up with an example where it's not true. And yeah, that's the example here. In fact, you can make it like really, really bad for A. You can make it like, you can make it quite awful for A, to be honest. So for example, you could have chosen, yeah, I think you can have chosen like 1 out of 1 in the second part. So for example, I think if you do a different table altogether, if you do like an A, like you can make it really bad for A in some sense. If you do like a 1 out of 1 is bigger than 98 out of 99. and then you have a 0 out of 1, and here you have like a 1 out of 99. Then you have like the whole thing is 2 over 100, so A has a terrible average, which is much, much lower than B's average of 98 out of 100. So yeah, you can do like really funky things with it. Like you can make the difference as large as you want between their performances. So yeah, the statement can be like spectacularly false as well. It doesn't have to be false in like an 81 to 98. It can just be like really, really false as well. So yeah. And that's kind of the point, is like if you come up with this extreme example early on, immediately you'll see what's happening, right? So if you had a statement which resisted extreme examples, then you can be more confident it's a true statement. Yeah. Okay, so that's question 5. Being an IMO, Olympiad mathematician, and winning a medal at the IMO. I think just enjoy doing maths should be, I think that should be the goal in some sense. And, you know, other things of that sort follow. But yeah. So for question 6, okay, so someone asks for question 6. Okay, what should we do next? Should we do question 6 or should we do 3, 4? Which one should we do? So there's a lot of threes in chat. There's a lot of threes. It's like 2 votes for 3, 1 for 4, 1 for 6. I'll wait for a couple more votes so we have a definitive we're doing this question. So many people want to do question number 3 at the moment. There's a bunch of threes in chat here. I'll just wait for like 1 minute. That's tough crime. Yeah. So yeah, there's question 6, there's question 3. Yeah, they're just waiting for, okay, there's a bunch of 6 now, so now it's equal. Now it's equal. The votes for 3 versus 6 are equal. So let's see. The votes for 3 versus 6 are pretty evenly matched right now. 3 is in the lead. Okay, 3 is definitively in the lead now, so it's pretty clear now. Pretty clear now that we. Yeah. The answer for 6, if you leave, I won't shoot. If you leave, I won't shoot. If you leave, I won't shoot. I have to think about that. I don't think so, right? Because if you leave, I won't shoot, then everyone just leaves, right? So yeah, I mean, then I think everyone leaves, right? Because they can. But like you're thinking the structure you're thinking is correct. It's just like the exact opposite of something. Like if you just like flip it around, you'll have something which is correct. Process. So we'll end at 4 p.m. So we'll have about 50 minutes. Three seems to be the majority. So we'll do 3 and then we'll do 6. How about that? 3, then 6. I think someone mentioned an answer to me in DM, which looks correct. I don't remember the answer, but we can figure it out. So we'll do it in this order. Yeah. Okay, we're doing 3, then 6. So we have this magical island where we have a bunch of lions. And then we have, I don't know, let's say we have n lions. I don't know the exact number we are using. And 1 sheep. And then we can figure out from there what happens. So now the rule is as follows. If a lion sees a sheep, lion eats the sheep, right? Straightforward. But the magical island does the following thing where if the lion eats the sheep, the lion becomes the sheep as well. So it's a pretty strange island that this happens in. And so every lion has the choice where they can eat the sheep if there's no risk to them, if they have no logical way of getting eaten afterwards. But if they eat the sheep and they know that logically they'll get eaten afterwards, they'll prefer not to eat the sheep. They'll prefer to stay away, stay alive. So what should the lions do is the question, right? And let's do small cases. So this is one important thing, which really just helps you in a lot of mathematics onwards. You should always try small cases first and then make conclusions later on. So if it's 1 lion and 1 sheep, this lion has no fear at all. They just eat the sheep and become the sheep. So there's just 1 sheep left at the end of the day, right? This lion just eats the sheep and that's the end of the day. So one case, when 1 lion and 1 sheep is obvious. All lions could share the 1 sheep, yeah. And that's not part of the question, but that's the more logical solution than whatever we have here. Yeah, but okay. So 2 lions, 1 sheep. This is the more interesting case. This is the case n equals 2. Will either lion want to eat the sheep is the question. if line 1 and line 2, if line 1 eats the sheep, then line 1 will become the sheep, and then line 2 will eat line 1, who's now a sheep, right? So line 1 has no reason to eat the sheep. Like line 1 knows if he goes there, he's going to get eaten in the next turn. So line 1 will not do that. And line 2 will also not do that because he has the same logic. So nothing happens. Nothing happens now. The sheep is safe. Despite 2 lions, the sheep is safe. Right? So this is actually pretty impressive. The sheep is completely safe with 2 lions. What about 3 lions? So if you have 3 lions, line 1, line 2, line 3, and you have 1 sheep, line 1 knows that if he eats the sheep, line 2 and line 3 will not eat him because they both have the fear of dying, right? So line 1 will then eat the sheep and then just completely chill after becoming a sheep. So this will become the line 2, line 3, line 1 is a sheep now. I'll just say line 1 is a sheep. Yeah. Okay. Yeah. So for 3, there's a reason where he can deduce that the other 2 will do the previous case, so he can safely go there. Similarly for 4. Now if you had 4 of them, then line 1 knows that if he eats the sheep, then one of line 2, 3, and 4 will also eat line 1, and then okay, they go back to it. So line 1 will not do that, and similarly none of the other lines will do that. So you'll end up in a situation where none of the lines will want to eat 1 sheep if there's 4 of them. And so now we're starting to notice a pattern where if there is 2 sheep or 4 sheep, nothing happens. The sheep is completely safe. And if there's one sorry, I said sheep. If there's 2 lions or 4 lions, nothing happens. We'll end at 4 p.m. So it's about 50 minutes or 45 minutes more. Yeah. So if you have 2 lions or 4 lions, nothing happens. If you have 1 lion and 3 lion, the sheep gets eaten by the fastest of them, let's say, and then the rest of them don't do anything. Right? We reduce to that case. And so you can prove this in general. So you can prove in general that if n is odd, then 1 lion eats the original sheep, let's say OG sheep, and becomes the new sheep, and nothing happens after. Nothing happens afterwards. Oh, it's actually not a whole slaughter. It's not like everyone dies, right? Because once the first lion eats it, now n it's even because you've reduced the number of lions, and now nobody touches that 1 lion. So it's just like at most 1 sheep dies at the end. That's like that's the worst case which can actually happen. Happens after. So this is the n odd case, because this was n equals 3 case, right? And n even, nothing happens. Yeah. And even nothing happens. And so this is the correct answer. And now once you have this answer, you can try proving it. So if you're more rigorous, if you like doing details more, because we have only done this for 1, 2, 3, and 4. We have only done this for n equals 1, 2, 3, 4. Maybe we can do it for 5. But we need to come up with an argument which generalizes this for all n, and then we can answer our original question, right? So right now, this is just a conjecture, which is correct. It's completely fine, and it's not very difficult to see that this is true. But you need to prove it. And so the proof is generally by induction for this kind of stuff, where you assume the statement is true for all n less equals m, and then you prove for m plus 1. So this is the principle of mathematical induction, which is, I think, quite common in Maths Olympiad. It's like a starting point of this type of stuff. So proof for m plus 1. And so to prove this thing for m plus 1, what you can do is, okay, to prove this thing for m plus 1, you can say that, oh, if m plus 1 is even, then you can go 1 step back because nothing will happen. Yeah, so for the odd case, because the odd case threatens something to happen, so none of the lions will take the sheep because then they'll be eaten by the m case. And if m plus 1 is odd, then one of the lions will take it because with the even case for m, nothing will happen. So you already have that information. So you can complete that proof if you want, write it out properly. And this is proof by mathematical induction. But this is the main argument. The argument which is true for 3 and 4 is the general argument which extends to all n. And so the answer just depends on the parity of n. And that's question number 3. Yeah. So it's quite surprising. Like you would expect that there will be a chain of eatings, right? Like you expect that one lion eats the sheep, then the other lion eats that lion, and so on. But really, it's just like either the original sheep gets eaten if there's an odd number of lions, and if it's an even number, nothing happens. Like they don't actually do any damage. Yeah, 4 o'clock. Yes, that's correct. Okay. Okay, so that's question number 3. Any questions about problem 3? Or we can move on to problem 6. No lion will ever eat the sheep. Let me check the number. I think this was 2024 lions. Yeah, so I deliberately chose an even number of lions. So someone, I think the first person who answered the question said that no lion will eat the sheep, which is correct. Yeah, so you DM'd me sometime back, but yeah, that's correct. Yep. 9th. So there is, now we have a 6 versus, so either we're doing problem 6 or there's a vote for 9th. Let's see if we do one. So what about if you want to do problem 6, problem 9? 6, there's a bunch of votes right now for 6. There's like 3 votes for 6 right now. Let's see. 6 and 9 are both actually pretty interesting. I would say 9 is probably the hardest problem on this whole thing. 9, I think, is genuinely extremely challenging. It's really, really fun problem. But 6 is like a sort of stepping stone towards the kind of idea needed for 9. Although not exactly, but yeah, kind of. So there's a lot of votes for 6. Let's go with 6 first. Yeah. So let's go with 6 first, right? Okay, so you have this one warden who has only one gun with one bullet. So really not doing the best with the security in this prison. And you have 100 criminals who want to run away, right? 1 to 100 who want to run away. And so each of them is smart enough where they want to run away if they can guarantee not being shot. But if they are uncertain that they'll be shot, then they won't run away, right? So what should the warden say to make sure that none of them leave, that all of them are scared enough where they don't want to leave? And so this is a pretty one-liner problem, so it won't take much time. But the idea is that, okay, let's say you label the criminals from 1 to 100, you number them. If you always insist, okay, let's try to motivate this because the answer is just one line. Let's try to motivate this. You always want everybody to be uncertain that they can be shot, right? So everybody should have that uncertainty. So you have to start from ground up. Let's say criminal number 1 should have the uncertainty that they can be shot. So what can you say which invokes that fear that, oh, 1 can get shot? And then similarly, if criminal 1 is not planning to run, then criminal 2 should have that uncertainty and so on. Yep, so the first DM I get is correct. So I'll shoot the first 2 leaves. Yeah, so I'll shoot. You can either say the first 2 leaves or one with the smallest label or something. So I say one with smallest label or whatever. Yeah, multiple could leave at once. Yeah. No, but here's the point. So when you say I would shoot the one with the smallest label, yeah, then one will never leave, right? Because one knows that one will always get shot if one leaves. So this is like complete certainty for one. Yeah, the labels are important. I think if you don't have labels, then of course you can't make the correct deductions then. But now one knows that if one leaves, one will be shot. So first he has to say within his statement that I'm giving you these numbers 1 to 100, and then yeah, you can do this. Yeah, you can make it precise. What if they can't be distinguished? Hopefully they can be distinguished, yeah. But the one who leaves first, yeah, kind of thing also, yeah. But the main point is that, okay, one now has the absolute certainty that one will be shot. Like if one leaves, there's absolute certainty that one will be shot, so one will never leave. And everyone else knows this. So 2 knows that one will never leave. So now 2 has the absolute certainty that if 2 leaves, 2 will be shot. And so on, all the way to hundreds. Nobody ever leaves. Because now they have the absolute certainty they'll be shot, right? Because I guess in the problem set, I didn't word the question perfectly. Because for example, if you say I'll shoot the first one who leaves, that is enough of a deterrent, but there's also like uncertainty, right? So if I think if I word the problem slightly differently, then if you don't have these labels to distinguish people, then they can leave and not have complete certainty they'll be shot. But now one has complete certainty that one will be shot, and two has complete certainty he'll be shot because he knows that one will not leave. And similarly, three knows that one and two will not leave, so three has complete certainty, and so on. So all of them are completely sure they'll be shot, even though only one of them could be, which is kind of the sort of miracle of this. And what exactly changed here is kind of the point, is that there was common knowledge, like all of them know this information. He announces it to everybody. And that's, I think, the key point here, is that if only one knows this and two to 100 don't know this, then you actually don't have 100% certainty they won't want to leave. But now nobody wants to leave. Like now everybody is certain they'll be shot if they leave. So yeah, I think the statement could have been worded better, but this is like one idea in some sense. It's not like a full problem, it's just like one idea of this. And I think 6 is kind of the culmination of this idea into a much more comprehensive induction type of thing. But yeah. You can even say I'll shoot one with the largest label. As long as the order is there, it doesn't really matter. As long as there's some ordering, it doesn't really matter. And in this particular instance, I think it's probably fine to even say timing. But yeah, just any ordering is fine. We can do 9 as well. So we can do 9 as well. What's the current vote? So do you want to do 9 or something else? 9 versus, let's see, what do we want to do? There's a bunch of 9s in the hardest somewhere. Yeah, no, 9 is the hardest for sure. I agree. 9, I think, is the hardest. Yeah, the 9 seems unanimous, which is great. Secure with one word, but it's not practical. It's not practical. Like I mean, most people see his thing. The reason this problem works is because all of these criminals are extremely logical. Like they are doing the perfect logical deduction, which is why they're not leaving. But in practice, people don't make perfect logical deductions, right? So then one bullet is insufficient. Like if you have 100 extremely logical people, one bullet is sufficient. But if you don't, then that's a problem. So yeah, so it is quite funny. It is quite funny in that sense, as you say, as you said. It is quite funny. So 9 is the verdict, then there's not even a versus. Like nobody even suggested another problem. 9 is the verdict now. So let's do problem 9. So problem 9 is a very funnily worded problem where it says that, okay, you have an island with 100 blue-eyed people. So it's a strange, mysterious island, as all of these problems are located on mysterious islands. So you have 100 blue-eyed people. We know this. So we know that all of them have blue eyes. But they don't know that they have blue eyes. No individual knows they have blue eyes. Knows about themselves. So no individual person knows that they have blue eyes or not. But they see everybody else. But they see everybody else. Yeah. So, oh yeah. So someone DM me what you say is correct, but I'll not spoil it by repeating what you said. But what you said is correct. See everyone's. So any individual person on this island does not know that they have blue eyes, but knows that all 99 of the other people have blue eyes. Yeah. So right now they have, and they have a custom, they have a tradition to maintain this level of uncertainty. So they have a ancient rule or a tradition. If anyone ever learns this, if anyone ever realizes they have blue eyes, so they all sleep at night, wake up at day, like usual. If anyone realizes they have blue eyes during daytime, let's say during daytime, they leave at night. They leave at the same night. Right? Same night, sorry, same night. So if I label them 1 to 100, if person 37 realizes that they have blue eyes, for some reason, some mysterious reason, they realize that this is true, then they're obligated to leave the very night when everybody else is asleep. So everybody else will know they left in the morning, but they won't know in the night. Like everybody else is sleeping. And if person 37 and person 53 both realize it on the same day somehow, then they both will leave, but nobody else will know at the night. They'll only know in the next day, in the morning, right? So that's the clarification here. So this is their tradition. This is their absolute rule. And because nobody is allowed to ask questions about it, and they can't ask questions about their own eye color. So I can't ask you, what is my eye color? What do you see? You can't say, you can't ask anything like that. Can't ask questions. This is also part of traditions. Yeah. Now, one day a stranger comes to this island who we assume is completely truthful. The stranger comes to this island and stranger says, I see one person with blue eyes, to everyone. So the stranger stands in front of all 100 people. Yeah, no, the stranger just comes, does this in the morning, leaves, and never is seen again. I see someone with blue eyes. And then the stranger leaves. And they say this in front of all of them, in front of all 100. Now the question is, what happens? So the question is, what happens to the island population? So it seems that nothing should happen, right? Because nothing should happen is what it seems like. That seems the very obvious way of looking at it, right? Because before the stranger thing ever happens, it's very clear that nothing can happen. Like there's no way they can ask questions. So they literally can't know that they have blue eyes. Nobody will ever know that. And so they'll all stay on the island because of the tradition or because of just not being able to ask questions. Now, stranger, when they say, I see someone with blue eyes, they also don't give much information, right? They don't say, oh, you have blue eyes. Like they don't point to anybody. They just say, I see someone with blue eyes. And then they leave. So the stranger, like all you can know is at least one person has blue eyes, but there's like 99 people you already see in front of you who have blue eyes. So how do you ever deduce anything from this, right? But the question asks, what happens to the island population after the stranger leaves? Like what change transpires? And the answer is extremely surprising. No one will leave. Yeah. So, and the chat is or DMs are pointing out more accurately that, or precisely that, okay, everyone else sees people with blue eye color. And so they won't think that they're the one accused. They see 99 other people, right? So why would anybody leave? Like nobody has any reason to ever leave, right? Yeah. But then we have a very good DM as well. So everyone knows, everyone else knows, and so on. Yep. That is indeed relevant here. Yeah. So in such problems where there's too many people, let's try to do small cases. That's one of the core intuitions as a mathematician is you should always try to do small cases. So let's try to do small cases. And notice something interesting. So let n be the number of people. Number of people. Okay. Yeah. Then if n equals 1, if you only have one blue-eyed person, and stranger says, I see someone with blue eyes, that person leaves the same night. So after one day, leaves. Okay. What about n equals 2? So if you have two people, A and B, and they're told that someone among them has blue eyes, right? So what happens on the first day? Well, first day A sees B has blue eyes, B sees A has blue eyes. First day, nothing can happen. First day, they both have to stay. Like they can't really leave on the first day, right? But second day, something interesting happens. A sees that B has not left, and B sees that A has not left, right? So when A realizes that B has not left, that means that B saw A must have blue eyes, right? Because if B, so let's do this deduction. We do A and B. Okay, let's do this. On second day, if A had any other eye color apart from blue, then B on the first day should have left. If A not blue, B should have left. Night of day one. Because then if A did not have a blue eye color, B would have immediately realized, because B sees A's color, right? So B would have realized that, oh, A does not have it, so I have it. So B would have left night of day one. So B would have left night of day one. But B did not leave night of day one, which means A must have blue. So A realizes on day two A has blue. And by the exact same reasoning, B realizes on day two that B has blue. And so they both leave on day two. Both leave on day two. Yeah. So now things are getting interesting. Things are getting pretty interesting now, right? This is an unexpected conclusion. This is a very strange conclusion. We expected nothing to ever happen, but just for n equals 2, on day 2, everybody leaves the island. Like both of the people leave the island. So does that change your opinion of what the answer should be? Like, does that change what you think is correct? So comments in chat, please. I just want to see, what does that suggest to you? What do you think the answer should be now after learning this day 2 secret or n equals 2 case? Does that change what you think should happen at the end of the 100 people case? Yeah. I'll do one more case and then I'll sort of hand wave a generalized argument, which I'll leave people to complete because it's a good thing to complete on your own. It's a really nice technical detail to complete. But I'll leave, yeah, day one again. Okay, yeah, I'll explain again because I think this is an important explanation. Like once you understand n equals 2, n equals 1, 2, 3, you pretty much understand everything, and then I'll just leave you to do the induction argument or whatever. Right? So yeah. So n equals 1 is just one blue-eyed person, and the stranger comes and tells them they see someone with blue eyes. The person leaves immediately, right? Like n equals 1, the person just leaves without even thinking because they know that it's only about them, nobody else is involved. N equals 2 is the first case, which is actually interesting because now there's uncertainty. Now they don't know about themselves. So A and B are both there. On the first day, A sees B has blue eyes, B sees A has blue eyes. There's no reason to leave. Like they don't actually know anything, right? There's no reason to leave. But on the second day, when they wake up in the morning of second day, notice the following. A realizes the following. If A did not have blue eyes, B would have seen A and B would have been like, oh, A does not have blue eyes, which means I should have I should be the only one with blue eyes because there's someone. And then B should have left on the night of day one. But because B has not left on the night of day one, that means that A cannot have not blue eyes. So A must have blue eyes then. So A realizes A has blue eyes. And similarly, B realizes B has blue eyes. Yeah. Similarly, B realizes B has blue eyes. So on day 2, both of them leave. On day 2, both A and B leave simultaneously, which is very interesting. Like this is an unexpected thing. We did not expect anybody to ever leave, but then on day 2, both of them left when there were just 2 people. So as someone mentioned in chat very correctly, on day 100, you will expect that all 100 of them will leave and nothing will happen before that. But let us try to understand why that happens. Like it's not just that we are trying to sort of metagame the answer. We also should understand why that process, what the process looks like, because it's pretty interesting. It tells you a lot about the kind of logic used here. So let's look at n equals 3, and which is actually the case which tells you what the continuation of this argument is. And you have 3 people, A, B, C, right? Okay. And so on day 1, obviously none of them will leave because, yeah, they just don't know. On day 2, A will see that, but A will still not be certain. A will still not be certain that B has not left because of him. B could have not left because of C as well, right? But on day 3, something interesting will happen. On day 3, what will happen is C will realize, oh, if C did not have a blue color, if C was not blue, so on day 3, this is what will happen. C will make the following deduction. If C was not blue, then A and B would have discarded C from their calculation altogether. So A and B should have left on the night of day 2. Like if C did not have blue color, then this is just about A and B being the blue people, and C has no business with this stuff. And so A and B should have left after day 2, at the night of day 2. But they're here in the morning of day 3, which means that C must have blue. Not possible. So this implies C must have blue. And because we did this deduction for C, same thing will apply for A and B as well. They will deduce the same thing for A, will do the same thing for B and C. B will do the same thing for C and A. So on day 3, all of them realize that, oh, they have blue color. So all leave on day 3. And this is the general argument, is that if you have n equals, or if you have any n number of people with blue eyes on this island for the problem, nothing will happen for the first n-1 days, and then on day n, everyone will leave. More generally, if you're on an island where there's n people with blue eyes and k people with red eyes or something, then also after n days, all the blue-eyed people will leave, and before the nth day, nothing will happen. So you can have people who don't have blue eyes and they don't affect the calculation at all. Like they don't really affect the deductions at all. So as people mentioned in the DMs, on day 100, everyone will leave, and before that, no one will leave. That is the answer for the problem. So, but there's still something to be done, which I've not done here, which I'll leave as an exercise, is that we've only proven it for day 3. If you want to really test your understanding, you should try to give an induction proof. You should try to say that, oh, suppose it is true for n equals k, proof for k plus 1. And the same argument applies that for 3 versus from 2. So the same step from 2 to 3 is what applies for k to k plus 1. Proof for k plus 1. And the idea is that, oh, on the k plus 1th day, every person will see that if they did not have blue eyes, the game should have ended on day k. Because it didn't, that implies that, oh, they have blue eyes and so on. So that's the 2-line induction step, which is identical to the reasoning for n equals 3. But you do that, and then you completely understand the problem. So yeah, that is the conclusion. That solves problem 9. So any questions? Yeah. Are people okay with this so far? Does everybody follow along? But it is quite surprising, right? So the follow-up question will be, what exactly did the stranger do which made this happen? And strangers did not say anything revolutionary, right? Like, why did people leave suddenly? Like, what exactly changed their information? So this is a follow-up question to test your conceptual understanding. What exactly changed? What exactly did the stranger do that made this happen? That's a pretty interesting question, right? Because if the stranger never came, then all of us agree that they never would have left the island. And now after 100 days, they all left the island mysteriously in some sense, right? So what exactly did the stranger convey? They just said, I see someone with blue eyes. But why does that convey so much information? Yeah. And the answer to that is, it's common knowledge now. Like this is something which everyone knows. Now this is something which all the islanders know. And everyone knows that everyone else also knows. And everyone knows that everyone knows that everyone else also knows, and so on. Like this whole chain of things. This is the maximum information you can extract from what the stranger said. And so now everyone realizes this chain of deductions. Yeah, everyone knows that everyone else knows, and so on. Yeah. So it's kind of like that whole movie trope that I know what you know that I know that, so on, right? So it's a pretty common trope, but this is precisely the information the stranger conveyed in this problem. So it's a good way of intuiting that. Oh, so someone has a question for day 3. Oh, but C will not leave in the night of day 2, right? Because yeah. Yeah, no, so it's like, okay, multiple people can leave at the same night. I think that's where your question comes from. Yeah, multiple people can leave at the same night. As long as you realize your own eye color, you can leave. Like you realize you have blue eyes, you can leave. Consent answers for all problems. Yeah, I mean, I think whatever we can discuss today, that's good, but otherwise you can try the rest of the problems and we can see if we have a reset script or something. Yeah, for sure. We can look into that. But yeah, this is the crux of problem 9. And that's why I think problem 9 was the sort of most difficult problem on this set. because it uses all of the ideas you built up in, say, problem 6 or before, and sort of just like combines them in this nice like induction plus sort of deducing things from negations and so on. So it's, I think, the starlight or highlight problem for this problem set. So what other questions do people want to try? Or do you have any questions on this one? Or do you want to try something more? Any recommendations? We can talk about that in like a Q&A once the recording is over or something. But we can, for now, just do like more questions. We can talk about like the IMO preparation stuff separately. Yeah. But yeah, so what's the next question people want to try? Like, let's have a poll. Let's have a poll in chat, please. So do we want to have... So let me look at the problem set and let's make the choice easier for everyone. So we did problem 6 and 9. We can do problem 10 or 12. I think both of them are quite interesting. So 10 versus 12. I think we only have time for one more problem, so we have to pick one and stick to that. So which one do we want? Like, can we have a poll in the chat, please? I think these are both quite fun. 10 is, I think, the harder one. 12 is, I think, a bit easier. There's a bunch of 4. Okay, there's a versus 4. Yes, because 4 has been on the requests for a while now. So let's see. 4 is also, I think, quite good. It's a bit different. So let's have more votes, please, because then we can actually make the final conclusion. So there's more votes for 4 suddenly, which is also good. Oh, wow. Okay. So 4 is suddenly leading by a huge margin. 10 is trying to catch up. Okay, it's a bit evenly matched right now. Let's see. 4 versus 10, guys. 4 versus 10. Let's go. 4 versus 10. Yeah. So someone asked in DM, how do you approach a problem? Yeah, I think small cases is generally a very good thing to look at, especially when you're doing like logic or counting or combinatoric extract problems, or even generally, I think it's a good idea to look at specific cases because that gives you like some sense of what should be happening. Like, it's not like a technique. It's not like it's guaranteed to work. It's more like a heuristic where this will hopefully tell you what should happen. It's a bit more like hopium there, but it's actually quite useful to do that. Oh, so there's also versus 8. There's a lot of conflicting opinions in chat. I think 8 is the Ramsey theorem, so it's a bit more standard where you can probably just like look it up in some sense, where you can look up the Google for that. But 8 is also quite interesting for sure. 10. So there's 10, there's 4. I think 4 is leading. Yeah. Oh, yeah, if you want to unmute and say something, it's also fine. That's completely fine. And 1. Okay, so 12th. Okay, 10. 10 seems to be the winner right now. So let's go with 10. And 10 will probably be the last one we can do, unfortunately, because we don't have too much time. I think 10 will take a while. Yeah. So let's try to finish 10. Okay. Say 2 logicians who have numbers from 1 to 30. And this time the numbers can be the same as well. We don't really know. So A and B. And let's say the numbers are little a and little b. Okay. Now let's look at a bunch of statements. So A asks, is your number double mine? And then B says, I don't know, is your number double mine? And A says, I don't know, is your number half mine? B says, I don't know, is your number half mine? A says, I don't know. B says, I know your number. So just by asking these questions, B just magically knows A's number, which is crazy. And both of them know that their numbers are between 1 and 30. So that is common knowledge. Both of them know this. So now let's try to understand how this works. So let's try to look at each statement and what does that statement tell both of the people. So A asks, is your number double mine? Which means that A asks whether B is equal to 2A. And B says, I don't know, followed by something. So I don't know is yours. So we'll ignore the is yours part for now. But what does the I don't know tell you? Can you say something from the I don't know? Like A asks, is your number double mine? And B says, I don't know. Does that tell you something? It can be double. It tells you it can be double or something, which means, can you say something about the number B? So B must be an even number. That is perfect. Exactly. So B is even. Yeah. And then now A, okay. It's not exactly 50-50 though, right? Because it's like, if B was an odd number, if B's number was 29, B knows for a fact that his number cannot be double of A's. So he won't say, I don't know. B will say, oh, it's not. Like, yeah, it's not double yours. We'll just reply logically and truthfully. So I guess this was implicit when they said two logicians, because they will give the perfect answers which are truthful. So if B's number was 1 or 29, B will, or even like 13 or something, B will just say, I know it's not double yours, and not like, I don't know. So I don't know means that B's number must be even, but even numbers can be like, oh, there are many even numbers. It doesn't know which one can satisfy the condition. Like he has no way of knowing. And now B asks the same, is your number double mine? And A says, I don't know. So A's number is not just even, A's number must be a multiple of 4 is the claim, right? Because B's number is even. Like A knows that B's number is even after the I don't know. And so when B asks, is your number double mine? Is your number double mine? And A says, I don't know. A replies with I don't know to this. But A already knows B's number is even. So if A's number was 2 modulo 4, if A's number was 6, then A's number cannot be the double of B's number because B's number is already even. So it will be a multiple of 4, what he's asking for. And so A's number has to be a multiple of 4. This is multiple of 4. So a multiple of 4. So it must be in the, we can write out possible candidates for A's numbers. 4, 8, 12, 16, 20, 24, and 28, right? Now let's go for the next statement. Let's go for the statement which follows after this. A asks, I don't know, is your number half mine? So A asks if his number is, if B's number is half A's number. Yes, I don't know part tells you it's a multiple of 4, but is your number half mine? Which means that, and B says, I don't know. So B says, I don't know. Which means that B's number can be half of something, right? So B's number can't be more than 15. So B has to be less equal to 15. Because if B's number was more than 15, then it certainly can't be half of A's number. So he would know, right? B's number is less equal to 15. And then B asks, is your number half mine? And A says, I don't know. So A's number cannot be, so A's number has to be less equals 15 as well, because I think more wouldn't make sense. But maybe we can say even more. So A's number now is 1 of 4, 8, or 12, based on less equals 15. So A's number is between 4, 8, and 12. Yeah. Mine, I don't know. I know your number. But also not just this. You don't just have A's number is less equals this. A's number has to be less equals 7 in fact, or less equals 8 in fact, right? Because or no, actually okay, I'll make a bunch more tinkering here. So A's number is less equals 15, but we'll actually say something more. B's number is even as well. We know it's even and less equals 15, so B's number is actually less equal to 14. And so if A's number was more than 8, if A's number was this, then A knows for a fact that his number can't be half of B's, because then 2A is at least 16. That can't be the case, right? So this implies A's number has to be less equals 7. So not only do you have less equals 15, you actually get a stronger less equals 7. And when you compare the less equals 7 with this, the only possible candidate for A's number is 4. So this implies A is equal to 4. And this is exactly what B deduces. So A's number is 4. Yeah, exactly. If it's 8, then it can't be half of a number less than 15. Exactly. That's precisely correct argument. Yeah. So A's number is 4. And some people actually deduce this as well. So it's a pretty good problem. I think it's very surprising that just from these statements, which are seemingly vague, because you can rule out a bunch of stuff. You can say that it can't be this. By that process of ruling out, eventually you are able to get to a limited set of values. And turns out there's a unique answer to that. So A's number can be determined very clearly. Yeah. Does everyone follow this statement? Everyone follow this solution? Perfect. That's good. That's good. Yeah. So we actually do have a bit more time then. Oh, that's good. We can do one more problem. But if you have any questions, just ask in chat and we can do a bunch of more problems. Like maybe one more problem. I think that should be all we can afford to do now. No, he didn't know that when A said if it's double. But then when B says I don't know, then the only possible way for B to not know would be then B's number is less equals 15. So once you have B is less equals 15, that's the thing which is logically true. So both A and B know this now. Like it's a thing because both A and B are logicians, they can sort of deduce that even before asking the next question. So implicitly, what you're saying is that before each statement, the person considers all possible logical things and knows what's the only possible sort of space of things where the answer can be. So they're actually like pruning while they're asking questions. And does that answer your question? I think someone in chat asked that when it said it doesn't. Yeah, thanks. Okay, that's great. That's great. Yeah. So if you have any questions, feel free to ask. Or we can do a poll for the last problem of the day, or we can call it a day as well. So it's up to the audience. What do you want? It's up to the audience if you want last problem of the day, or we can do a poll on that. Or do you have any questions on any of the previous problems? We can address them. Another problem? Sounds good. So what do we have in candidates? We had like 4 and 12, right? Let's do 4 versus 12. And so this is the final vote, final poll. So can we have a poll in chat, please? 4 versus 12. It's evenly matched right now, 4 and 12. It's pretty interesting. Okay, 4 seems to be leading right now. 4 seems to be leading right now. So let's see. Wait for 1 more minute and then we'll make the call. 12 is catching up. Oh, no, but it's the same person voting twice. So 12 is not actually catching up. Okay, so let's just do 4 then. Let's just do 4. Because 12 unfortunately didn't catch up. But okay, for 12, the type of logical argument you're using for 12 is pretty much the same for what you did for 10. It's like the same type of thinking, like different context, but same type of thinking. So 4, I think, is a slightly different anyway, so it covers more ground, I guess. Yeah. So king is doing this tax collection thing. And let's say, so the king has these 10 territories, 1 to 10, and he's collecting taxes from each of these places, right? So he wants like 1,000 coins from each of them, 1,000 gold coins from each of them. And now one of the people tries to lie, and they're like, okay, now instead of sending 100% gold, they send like 90% gold per coin. So each of their coins is 90% of the weight or something. So it's 90% of the total weight. So they're just like trying to scam the king. And the king has only one measuring device. They don't have like a balance. They just have like a digital weighing scale or something. Like I don't know what it's called, but you get like an actual reading. So you can put a weight on this thing. You can put like 100 kg and it'll show you 100 kg over here. So we'll assume each of these are like 1,000 grams or so on. or you can put like 20 kg. So he can decide to put any weight on this, but he can only do it once. He's only allowed to put one weight on this one time. And based on the reading on this scale, he has to decide which one, he has to know for sure which one did the scandal. So he has to detect who did the corruption here. So what's the strategy for this? So one thing is that if you treat all of the, like, one thing is that, okay, if you don't pick coins from something, if you don't, so like from each of these 10 piles, if you don't pick coins and from territory. Yeah. So someone has the correct idea. One by one. Yeah, one by one would be a bit of a problem though, right? Each bag one. Oh no, you can't do it one by one. So you're only allowed like literally one weighing. Like you're only allowed to do it once. Like you can't use the same, like the skill goes bust after the first weighing. So the idea that you can stack one bag and then keep doing the other bags, like that won't work, right? Because you're only allowed to do one reading. The second time you put a bag, it won't show anything. It'll only show things once. So yeah. Yeah. Okay, so here's the point. You can pick, yeah, even without removing. The point is it only shows one reading and it won't show a second reading ever again. So it'll only show one reading. Points from, yeah. So some people already have the correct idea. So I'll motivate with the correct idea, how you should arrive at the correct idea in this cases. So firstly, you have to pick a coin from every bag. If you ignore a bag completely, then you don't know for sure that that person did not cheat. Like that person could be the cheater and your reading will not say anything. So have to pick one coin from each bag. Pick from each bag. So this is unavoidable. Like if you don't do this, then you won't ever certainly be able to find it. Like you won't have the certainty that your estimation is correct, whatever you do at that point. So I had to pick from each bag. And if you pick the same number of coins from each bag, you won't know which one is the lighter one. Like you can't pick the same number from each. Number from each. So combining these two ideas together, you have the strategy that you have to pick a different number. So our strategy now is pick different number of coins from each bag. And so more precisely, pick one coin from one. So 2 coins from 2, and so on, all the way to like 10 coins from 10. So now you look at the total weight of this thing. And the total weight, if all of them were genuine, if genuine, the total weight would then be 1 plus 2 plus all the way till 10 times 10 grams. Let's say like each coin, or let's say each coin was worth 1 gram or something. The whole thing would be 1 plus 2 plus, or I'll say, okay, each coin is worth 10 grams. I'll just assume they are each worth 10 grams because that'll make the decimal part easier. So there won't be, assume each of them are 10 grams. It doesn't really matter what you assume. So the total weight would be 1 plus all the way till 10 times 10. So this is 550. So this should weigh 5.5 kg, or sorry, 550 grams, sorry, 0.55 kg, 550 grams. Now, if the seventh one was liar, if the seventh one was faulty, then instead of 70 in the sum, it should have been 70 is 90%. It should have been 63, which means should have been 7 lower. So whatever actual answer you get, you're supposed to get 550 if all of them are correct, minus the actual answer, you get. So let's say your actual answer was 543. Then you know that the person at the number 7 cheated, like they had the ones which were faulty. If the actual answer was 545, then you know person 5 cheated, and so on. So now you know precisely who did this. One coin from one collector, 2 from 10 from the last. Yeah, exactly. That's the strategy. So someone messages correctly. 1 coin from the first collector, 2 from the second, 10 from the last. Doing all this all the way. Check the difference between the theoretical price and the actual price, and then or actual weight. And the difference between theoretical weight and the actual weight is the number of the person who did the cheating. So you can very precisely pinpoint that. Yep, precisely. Exactly. If the weight loss is 0.1 ounces. Yeah, exactly. Or whatever unit of weight. Like the unit of weight, the gram, the ounce doesn't really matter. If the weight loss is like 1, then it's person 1. If it's 2, then it's person 2. If it's 10, it's person 10. So like the exact weight loss tells you who did it. So that's kind of the trick here. The precise loss in weight tells you who did it. And again, once you have the trick, verifying things is easy. Like verifying that this trick works is easy. Coming up with it is the tricky part. For that, we have these 2 heuristics, and this is kind of how you think about math problems in general. First, you realize that you have to pick one from each bag, and then you have to realize, oh, you can't pick the same number from each, because then you won't be able to distinguish between them. And once you combine these 2 ideas, you can play around with it and come up with the weights 1 to 10 for the respective people. Does that answer? Okay. I think many people came up with the solution themselves as well. So there's not much ambiguity. And with that, we'll end today's session. So I don't think there'll be more questions, but if you have any questions about the questions we discussed, we can still talk about them for a couple more minutes. But we'll end today's session. There won't be more problems for today. That's the end of the day. So I'll just close the whiteboard if there's no other questions. Let me know if you have questions. We can wait for 2 minutes. Yeah. 𝐼MO Q&A. 𝐼MO Q&A. That's a good question. I'll ask Professor Chanak. Maybe we can do it separately to the classes, because we can do it like outside classes, like general preparation stuff. So we can have like a sort of like a general 𝐼MO Q&A interview type of thing. It's like sometime after the classes are over for this season, this cycle. Yeah. Hope everyone had a good time. Hope everyone enjoyed. And if you have any questions, we can discuss them next time as well, or you can like compile your questions and give it to me, Professor Chanak, and I can just look at the questions afterwards. So yeah, thank you everyone. Thank you for coming. Hope you had a good time. I don't think other questions will be discussed next week. We'll do like a completely separate thing. But if you have questions about them, we can you can put them in the common questions, and we can like collect them and do stuff with that. So yeah, some of them we'll do more algebra type of thing, and maybe like some geometry afterwards. So, like some algebra next time, and then some geometry afterwards, just to like cover the very broad strokes for SLMC. Like it's not like comprehensive coverage. It's not like sufficient for the competition, but it's just like a flavor for all types of things in the competition. Yeah. So yeah, hope you have a good time. See you guys around. No worries. Thank you.